So what does rotational inertia have to do with torque? How do forces and torques change motion? All right, in this lesson we're going to be able to recite, explain, and apply Newton's laws for translation and Newton's laws for rotation. We're going to be able to draw an extended body diagram showing the forces acting on an object, and we need to be able to change the extended body diagram into a net force equation and a net torque equation and solve for an unknown. Newton's laws for rotation are almost the same three laws we had for translation. Remember those three laws? If there's no net force on an object, then the object's translational motion is constant speed and constant direction. That can be a zero velocity. If there is a net force acting on the object, then the object's center of mass has an acceleration, which is the net force divided by mass. So the acceleration for a center of mass equals the net force acting on an object or system divided by mass. So the F net equals mass times acceleration of the center of mass. And then finally, if A exerts a force on B, then B will exert a force on A in an equal magnitude and opposite direction. Same three laws, but for rotational motion. First law for rotation: if no net torque acts on an object, then the object will rotate at a constant rate. An example is the Earth, which rotates on its axis, giving us day and night. The Earth experiences no torques from objects outside of the Earth, so the Earth's rotation is constant. Every day is 24 hours. Newton's second law of rotation says if there is a net torque on an object, then the object will have an angular acceleration, according to the equation alpha equals the net torque divided by our rotational inertia, or moment of inertia. This can be written as the net torque equals I alpha. I times alpha. So remember, torque is our rotational equivalent to force. Alpha is our rotational equivalent to acceleration. That would mean moment of inertia is our rotational equivalent of mass. Remember that I is rotational inertia. So if an object has a lot of rotational inertia, it won't change its rotation very rapidly. Second law appears like this: alpha equals the net torque divided by I, or net torque divided by I. Finally, on to the last rotational law. If A exerts a torque on B, then B exerts a torque on A that is in equal amount and opposite in direction. Luckily, we got rid of that incorrect way of wording Newton's third law, that little poem rhyming-ish thing that you had learned previously in some other classes. Now that we have this nice definition, we can also apply the same exact definition to rotation. More on this law in the next unit.